See, now that we have looked at how to measure very large lengths using the parallax methods, or very small lengths, for example, the oleic acid molecule that we have measured, let us look at some of the common lengths that we encounter in daily lives and how do we measure those to great accuracy. So one of the methods of measuring lengths that you have been using is this foot ruler. Okay, so this is a ruler where we will look at if you look at the centimeter scale, so the centimeter, on the top I have centimeters, and each centimeter in turn is divided into 10 regions. Each of those regions is worth 1 millimeter. So using this scale or this ruler, I can really measure lengths up to an accuracy of a millimeter. Now that's good enough for normal usage. Now you ask, what if I want to increase the accuracy? So can I really divide this small millimeter into 10 more regions and be expected to be able to read those gradations, those very small gradations? You will see, you will realize that is almost impossible. Our eye cannot resolve such a detail. So using this particular scale, I cannot, even if I were to somehow divide this 1 millimeter into even smaller regions, I really cannot be expected to read those 1/10 of a millimeter that I have created. But of course, in our daily life, especially when we are designing small devices like phones, tablets, and smartwatches, things like that, we are expected to be able to read such small lengths with great accuracy. So we are expected to do that, but of course this ruler cannot do it. So how do we do it? So we have created special devices using which we can measure lengths with great accuracy. So special devices have to be created. We cannot just use the normal scale or normal ruler. And one of such devices is actually the this one. This is known as a screw gauge, and using a screw gauge, I can read lengths up to an accuracy of 1/100th of a millimeter. That is great accuracy. Okay, so we just have a model of a screw gauge right here, and if you notice, in this particular screw gauge, we really have two scales. There are two scales here. One scale is this linear scale that you see right here. So I hope you can see my little pencil here. Okay, so this particular scale, one of them is right here, and this is known as the main scale. Okay, so this scale is always known as main scale in all kinds of devices. This provides the main reading, the more accurate reading in the case of a screw gauge. So just to help you see better, I will just vanish. Okay, so just to help you see this device better. Okay, so the more accurate reading, the reading between these two main scale divisions, if I want to read those readings are provided by this rotational scale, the circular scale, and this is the screw scale. So there are two scales here, and the combination of the two readings on the two scales gives me the net reading in the case of a screw gauge. See, the way it works is, we'll just move this screw gauge in a second. It is there is an animation here. We'll just move it, but before we move it, let us just understand what it really means. See, these divisions, each of these divisions is worth 0.5 mm. Okay, and in moving from one such division to the next one, right? So if I move from here to here, this division, moving from here to here, this rotational scale, the circular scale, actually has 50 gradations. So those 50 gradations are traversed when I move from 0.5 mm on this main scale. So this 50 gradations of the circular scale is equal to 0.5 mm. So one gradation is equal to 0.5 divided by 50 mm, and this is equal to 1/100. Okay, mm. So notice that just by using this simple mechanism of screw, I was able to increase the accuracy to 1/100th of a millimeter. So now I can, on this scale, using this screw gauge, I can measure the lengths to an accuracy of 1/100th of a millimeter, which is very, very accurate. This another device. Okay, so we'll just do the animation, little bit of animation, because that's what I promised. So we will just drag this now, and as you can see, as it moves from one gradation to the next, there are 50 gradations on this scale, on our circular scale, and when it moves 0.5 mm on the main scale, those 50 gradations are actually traversed on the circular scale. So that is the principle of working principle of the screw gauge, right? But notice we just didn't divide this main scale further. We were not able to do that. We had to actually use another mechanism, a completely new, a novel mechanism to increase the accuracy of the reading, and that is a very important concept. You just cannot just divide the gradations further and further and be expected to read it with great accuracy. You just have to create a new device to get more accuracy. Now here is another such example. This is something that you must have seen it in the labs, and this is an example of a Vernier calipers. So Vernier calipers again use a different mechanism to increase the accuracy of our reading, and the way these work is, again, there is a main scale. So that is simple. There is a main scale which is right here, okay, and main scale, one reading is equal to 1 millimeter. The main scale is actually read by looking at the 0 marked here on the second scale, which is known as Vernier scale. So this is Vernier scale. So I look at the 0 of the Vernier scale, and wherever this comes, I am saying that is the reading of my main scale. Okay, so I am not reading 0 here. I am not reading Vernier scale yet. What I am saying, listen carefully. Wherever the 0 of this Vernier scale comes, that is my main scale reading. So for example, in this case, the main scale reading is actually equal to 0. Okay. Each of these gradations of the Vernier of the main scale, the 1 millimeter, is then further divided into 10 gradations, and those 10 gradations, where did they come from? They come from the Vernier scale. Okay, so those 10 gradations of the Vernier scale is equal to 1 millimeter of the main scale. Therefore, one gradation of the Vernier scale is equal to 1/10 of a millimeter. Okay, so this is 1/10 of a millimeter. So I am able to read using this Vernier calipers, and we will study how it actually works in a very different class. You can look at it. Okay, there we have looked at this Vernier calipers in great detail. But this what is the accuracy? The accuracy is 1/10 of a millimeter, and this is also known as least count. So least count of a Vernier scale is 1/10 of a millimeter. See, the Vernier scale is read by looking at, okay, so we'll just move this Vernier calipers a little bit, and that will give us some little bit of idea about how this happens. Okay, so look, what happens is I move this Vernier scale, okay, and Vernier calipers, and the Vernier scale is then read by it is not read simply by looking at the scale itself. I am not looking at the scale itself. I am not looking at this scale and saying that, oh, just where do I read it? Okay, so the way I read it is I look at the gradation on the Vernier scale which intersects or which lines up with the main scale gradation. So here 7 is lining up with this main scale gradation, and we have looked at it why this works in a separate class. So definitely search for that class and look at it. Okay, but the idea is that this 7 mark is completely lining up. Okay, no other mark is lining up so well as the 7 mark of the Vernier scale. So this 7 mark of the Vernier scale is lining up with any mark on the main scale, and therefore my Vernier scale reading becomes 7, which of course is 1/10 of a millimeter or 0.07 centimeter. So here all the readings in this animation are given in centimeter. So this is 0.07 centimeter. Okay, and the main scale reading, you look at it, it is this one. Okay, so 0, where is the 0 coinciding? 0 is coinciding. Okay, it is not exactly coinciding, but we look at 0 and we go before that. So before that, what is the first reading of the main scale? It is 0.1. So that is what I read. So why do I go from 0, and why do I go back from 0? Why do I look at the main scale reading going back from 0? Because further accuracy is provided by this Vernier scale. Above 0, how much I have moved? Okay, so this distance. Okay, so after 0.1, how much I have moved? My 0 has moved how much? That is given by this Vernier scale reading. So this is 0.07 centimeter. But here all I need is I look at the Vernier scale 0, and then I go back and I see what is the main scale reading. So that comes out to be 0.1. So 0.1 plus 0.07, and that is equal to 0.17 centimeter. Okay, so very accurately I have been able to read this in centimeters. Okay, so least count we have to understand, and there is another kind of error which is known as zero error. So zero error means that if I am making the reading of this 0, right, for Vernier calipers, what is the 0 reading? 0 reading is when these two are completely near each other, when the two calipers, when the two of its thongs are completely next to each other, that would be the 0 reading. So here the 0 reading is obtained when actually there is nothing between the Vernier calipers. So this is the 0 reading, and what is the reading? What is the scale? What does the scale tell me on this 0 reading? So scale in this case is actually equal to 0. So this Vernier calipers has no 0 error. So if the scale was reading something here, then we would have had a 0 error, and we would have to take it into account while doing the measurements. So this is an example of a Vernier caliper, and those two instruments are actually used to measure the lens to great accuracy, Vernier calipers and screw gauge. So those two are important. Now another such device which is also used to measure lens to great accuracy is this one. This is known as a spherometer. So what is a spherometer? The name itself suggests it. Spherometer is used to measure radiuses of spheres. So why is it used? See, the lenses, they are made or they are cut out from large spheres, and we only have a piece of that sphere. So when we are looking at a lens, we only have this region. We don't have anything else. So we have only the top portion of the sphere, let's say. And what do I want to do now? I want to measure the radius of curvature of that particular sphere, of that lens. I want to measure the radius of curvature. So how do I do that? I use a device known as spherometer. So what spherometer has is 3 fixed legs and 1 moving leg. And this moving leg I can move up and down by using this screw. Again the same thing, there is a circular scale, there is a linear scale. This linear scale is known as vertical scale also, and the circular scale is of course circular, or you can call it the screw scale. So this circular scale we move up and down, and one gradation on this linear scale similar to the screw gauge, it has the same principle. One division of this vertical scale is worth a number of divisions on that circular scale. So circular scale will give me my reading to great accuracy. The way it works is that I fix my 3 screws right here. Okay, so the fixed screws I put at a point on top of a, let's say, a lens, and then what I do is that I then move this circular scale up and down. The fourth or the moving leg, I move it up and down, and I using the difference between the fixed scale and this moving, the fixed leg and the moving leg gives me the difference in height between those two, gives me the total height of the lens. Using this height of the lens, then I can derive the radius of curvature of the sphere from which it was cut. And again, this is again very important, because again it has very high accuracy, and it is used quite a bit in the case of optics. So here we are able to see an example of a screw gauge being used to measure the depth of a concave lens. So this is a concave lens, it goes like this. Okay, and using this I am able to measure, what does it measure? It measures the difference in height between this moving leg and the fixed leg. So it is able to measure this difference in height, and with this difference in height I can then derive the radius of curvature of the lens, and that is used in optics. Okay, so with this we have covered all kinds of lens, all kinds of measurements of length. Let us now look at some of the lens which we encounter in our normal which we encounter in physics. So in physics we encounter lens which are very large, and we also encounter lens which are very small. So let us just take an example, some examples of lens which are very large. So here are the some examples. So here, for example, when we are looking at the galaxies and astronomical measurements, our lens become very large in that case. So those are some very large lens. So this is, if you look at the top portion of this table, those are very large lens, and we have to measure those. Of course, we are using various methods like our parallax method to measure those. And then we also have to look at very small lens, For example, the lengths of atoms, lengths of molecules, how big is a molecule, how big is a proton, and those lengths are very small, order of 10 raised to the minus 15 meters. A typical atom is on order of 10 raised to the minus 10. 10 raised to the minus 10 is actually 1 angstrom. Okay, so those are some very meter is equal to 1 angstrom, and this is the symbol of angstrom. Okay, it's another unit, very to measure very small atomic lengths. Okay, so we have to measure those also. So these are some of the range of values of length, and you would be able to appreciate that our accuracy in measuring the small lengths as well as the large lengths is actually quite good. So with using various techniques, we have been able to measure all of these to some degree of accuracy. Thank you.